Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be starting a brand new physical chemistry playlist. And my goal with this playlist is to break down the concepts of thermodynamics in a very clear and approachable way so that we can see how these ideas connect to everyday life. We're going to begin with an introduction and a quick review of important chemistry topics and terminology. So in this first chapter, we're going to work through four main objectives. First, we're going to ask, what is thermodynamics? Second, we're going to go over the units used in physical chemistry, and we're going to review force and pressure. Third, we're going to look at the concepts of atomic mass, molecular mass, and the mole. And then finally, we're going to define some introductory terms that are going to be used often in this course. This includes systems and surroundings, extensive and intensive properties, the difference between state and path functions, and the meaning of temperature, along with the zeroth law of thermodynamics. With this introduction in place, let's go ahead and get started with objective 1. What is thermodynamics? Physical chemistry as a discipline is often defined as the application of quantitative methods to chemical problems. That means we go beyond descriptions and instead measure, calculate, and model chemical systems in a way that lets us make predictions. Within this discipline, thermodynamics is the branch that focuses on energy and its transformations. When we study thermodynamics at this introductory level, we describe systems in terms of their macroscopic or bulk properties. These are measurable quantities like pressure, volume, temperature, and energy. Our approach here is going to be different from statistical mechanics. Statistical mechanics looks at systems from the microscopic perspective, using probabilities and averages over large numbers of particles to explain why macroscopic properties take on the values that they do. In thermodynamics, we instead focus on relationships between these macroscopic quantities. Both approaches are deeply connected, but for now, our emphasis is on thermodynamics, which again allows us to make powerful predictions without directly invoking the motion of every atom and every molecule. The strength of thermodynamics is that it applies to an enormous range of phenomena. To illustrate this, let's look at some examples of how the topics we're going to cover in this course connect to real-world applications. We'll start with work, heat, and the first law of thermodynamics. These form the foundation of energy conservation. Energy is neither created nor destroyed. It is simply transformed. Now, as an example, in a power plant, heat produced by combustion is going to be converted into electrical work. The same principle applies in biological metabolism, where the chemical energy stored in food is transformed into the heat and work that sustain life. Enthalpy is another central concept, and it describes the heat exchanged in processes that occur at constant pressure. And this is the condition most relevant to chemistry and biology. For example, the combustion of rocket fuel relies on enthalpy changes to produce the thrust that's needed to launch spacecraft. Entropy is another important topic. This is the thermodynamic property that captures the dispersal of energy. Now, beyond its role in chemistry, entropy is central to data compression in information storage, where it defines the limits of how efficiently information can be encoded. In biology, entropy plays a critical role in protein folding. Free energy, whether it's Gibbs or Helmholtz, tells us the maximum useful work a system can perform. And this concept is indispensable in electrochemistry, where it determines the work available from a battery. It's also super important in biochemistry, where it governs processes like protein folding and enzyme catalysis. Spontaneity and equilibrium are also core topics that we're going to discuss in our course, and they're essential to understanding how reactions proceed and when they stop. Industrial processes like the Haber process for ammonia synthesis depends on controlling equilibrium to maximize product yield. Even something as simple as the carbonation in drinks reflects equilibrium principles where dissolved gases balance between the liquid and the atmosphere. Phase transitions are another area where thermodynamics gives us predictive power. Refrigeration and air conditioning, they rely on the controlled vaporization and condensation of fluids. And weather patterns on Earth, they depend on the thermodynamics of phase changes in water vapor. Finally, chemical potential and mixtures are super important for explaining behavior, again, in both chemistry and biology. Adding salt to ice lowers the chemical potential of water, which causes the ice to melt. In living systems, osmosis relies on differences in chemical potential across membranes to regulate the movement of water in and out of cells to maintain homeostasis. So what I want to emphasize here is that thermodynamics is not an isolated subject. It is directly connected to systems and technologies that we encounter every single day. And as we move through the course, we're going to revisit these examples and really show how the principles of thermodynamics that we learn together explain and predict the behavior of so many different things. And that's objective 1 for us. So now we can move into our second objective, which is about units. The most common system of units we use in science is the metric system. And from this, the SI units is defined. SI units provide a consistent framework that scientists all over the world rely on. And this is especially important in thermodynamics, where precision in measurements and calculations is important. Now, in SI units, we divide measurements into 2 categories: base units and derived units. Base units are the fundamental building blocks. There are 7 of them that we use, and they are mass measured in kilograms, length measured in meters, time measured in seconds, temperature measured in Kelvin, electric current measured in amperes, amount of substance measured in moles, and luminous intensity measured in candelas. All other units that we use in science are constructed from these base units. Those are what we call derived units, and they come from combining base units in specific ways depending on what physical property we are describing. So for example, volume is a derived unit. If I calculate the volume of, say, a rectangular box by multiplying its length, width, and height, each of those measurements is in meters. And when I multiply them together, I get meters cubed, which is the SI unit for volume. Now, keeping that in mind, let's move into 2 quantities that are especially important for thermodynamics and also discuss their derived units. Force and pressure, those are very important. We're going to start with force. Force is defined as a push or pull on an object that can cause it to move or accelerate. In physics, force is formalized through Newton's second law. This tells us that force is equal to mass multiplied by acceleration. In words, if you take the mass of an object in kilograms and you multiply it by the acceleration, which has units of meters per second squared, you're going to obtain the unit of force, which we call the Newton. 1 Newton is equal to 1 kilogram meter per second squared. Force by itself is an important quantity, but in thermodynamics, we are often more interested in pressure, which builds directly on the idea of force. Pressure is defined as the amount of force applied per unit area. If we take a force in newtons and we divide it by an area in square meters, the unit that results is the Pascal. 1 Pascal is equal to 1 Newton per square meter. Now, in chemistry and physics, we often work with very large pressures, so the Pascal is a relatively small unit. Because of this, we frequently use larger or alternative units of pressure. For example, 1 atmosphere is equal to 101,325 pascals. This is also equal to 101.3 kilopascals, about 1.01 bar, 760 millimeters of mercury, 760 torr, or about 14.7 pounds per square inch. These are just different ways of representing the same quantity, and we need to be able to confidently move between them depending on the context. Now, how do we measure pressure experimentally? The earliest and most important instrument developed for this purpose is the barometer, which is used to measure atmospheric pressure. A barometer consists of a long glass tube that is closed at one end and filled with mercury. When the tube is inverted into a dish of mercury, the column of mercury inside the tube that's supported by the atmospheric pressure exerted on the surface of the mercury in the dish. Now, no air enters the closed end, so that means the space above the mercury column, that is a vacuum. At sea level, the height of the mercury column is about 760 millimeters, which corresponds to 1 atmosphere of pressure. This is why we often use millimeters of mercury as a unit of pressure. So the barometer measures atmospheric pressure. What if we want to measure the pressure of a gas sample in the lab? For that, we can use a device called a manometer. Manometers also rely on mercury or another liquid to balance pressure differences. But instead of measuring the atmosphere directly, they measure the pressure of a confined gas. There are two main types of manometers. You have the closed tube manometer. This is used when the gas pressure is less than atmospheric pressure. So in this setup, one side of the tube is sealed, so the difference in mercury levels corresponds directly to the gas pressure. This is in contrast to the open tube manometer. This is used when the gas pressure is equal to or greater than atmospheric pressure. In this case, one side of the tube is open to the atmosphere, and the difference in mercury height tells us how much greater the gas pressure is compared to atmospheric pressure. Now that is objective 2 for us. Let's move on to objective 3. Here we're going to talk about atomic mass, molecular mass, and the mole. To begin, we need to define a standard way to describe the mass of atoms and molecules. Individual atoms are far too small to be measured conveniently in grams or kilograms, so scientists use the atomic mass unit, abbreviated as AMU. By definition, one atomic mass unit is exactly 1/12 the mass of a single carbon-12 atom. Numerically, this corresponds to 1.6605 times 10 to the negative 27th kilograms. This standard allows us to compare the masses of different atoms and molecules on a consistent scale. From here, we can define atomic weight. Atomic weight is the weighted average of the masses of an element's naturally occurring isotopes. So in other words, most elements exist in nature as a mixture of isotopes, and each isotope has its own mass and natural abundance. The atomic weight reflects the average mass of the element, accounting for both the isotope masses and their abundances. Let's look at an example here and try to work through it so we can really visualize what atomic weight means. This problem says, if an element has two isotopes, isotope A with mass of 10 AMU and a natural abundance of 90%, and isotope B with a mass of 11 AMU and a natural abundance of 10%, what is the atomic weight? To calculate the atomic weight, we take the weighted average. That means we multiply 10 by 0.9, which gives us 9. And then we add 11 multiplied by 0.1, which is 1.1. Then we add those together and we obtain an atomic weight of about 10.1 atomic mass units. So this element that has 2 isotopes, the atomic weight is 10.1 AMUs. This illustrates why the atomic weights we see on the periodic table are often not whole numbers. They reflect the natural isotope distribution of each element, not the mass of a single atom. And this distinction is important because in chemical calculations, especially when we move into thermodynamics and mole-based calculations, we always use atomic weights as they appear on the periodic table. Now that we've defined atomic mass and atomic weight, we can extend these ideas to one of the most important concepts in chemistry, the mole. A mole is the link between the microscopic world of atoms and molecules and the macroscopic world that we measure in the lab. So by definition, 1 mole is the amount of substance that contains as many entities, whether atoms, molecules, ions, formula units, as there are atoms in exactly 12 grams of carbon-12. This number is known as Avogadro's number, and it is equal to 6.022 times 10 to the 23. And this is important to remember, and this value is really important to understand. It's a value that is similar to when we use the word dozen. Dozen always means 12 of something. So the mole, it simply counts entities, and the count is always the same regardless of the substance. Now, the usefulness of the mole, it comes from the fact that it connects particle numbers to mass. So for each substance, the mass of 1 mole in grams is numerically equal to its average atomic or molecular weight in atomic mass units. And this is what we call molar mass. So for example, the atomic weight of oxygen is about 16. So 1 mole of oxygen atoms has a mass of 16 grams. Similarly, the molecular mass of water is about 18. So 1 mole of water molecules has a mass of 18 grams. This relationship allows us to move between 3 different quantities: the number of particles, the number of moles, and the total mass of the sample. If I know any one of these, I can calculate the other 2 by using Avogadro's number and the molar mass. And this is best captured by doing an example problem and really working through this flow chart. So here I want to point out, if you want to move from number of particles to moles, you can go ahead and divide by Avogadro's number. If you want to go in the opposite direction from moles to number of particles, you're going to multiply Avogadro's number. If you go from moles to mass, you're going to multiply by molar mass. And if you go from mass to moles, you'll divide by molar mass. And of course, you can move through from number of particles to mass. And in that way, you're going to have to first divide by Avogadro's number and then multiply by molar mass. If you go in the other direction from mass to number of particles, you're going to have to divide by molar mass and then multiply by Avogadro's number. So in this way, we can understand how easily we can move between these measurements. This example problem says, suppose you have 3.011 times 10 to the 23 particles of argon. What is the mass of this argon sample? Now, to get mass, I'm going to first convert particles to moles, then moles to grams. We're going to start by writing down what we know. We know that we have 3.011 times 10 to the 23 particles of argon. We want to convert this to moles, so we are going to divide by Avogadro's number. 1 mole divided by 6.022 times 10 to the 23rd particles. You're going to see the word particles cancels out in the numerator and denominator, leaving us with units of moles. Next, we want to convert moles to mass. So here we're going to multiply by molar mass of argon, which is 39.95 grams per mole. Again, you'll notice when we set it up this way, Moles cancels, and it leaves us with units of grams. That's exactly what we want. So we know we set this up properly. Then we're going to plug this calculation into a calculator. We're going to get 19.98 grams, which I'm just going to round to 20.0 grams. So what is the mass of this argon sample? 20 grams. And with that, we've concluded objective 3. We can now move into our last and final objective. In order for us to really discuss thermodynamics, we need to discuss energy. Energy is the essence of our very existence as individuals and as a society. The food we eat gives us the energy to live, work, and play, just as the oil consumed by manufacturing and transportation systems power our modern industrialized civilization. And while the concept of energy is quite familiar to us, energy itself is rather difficult to define precisely. So in our lecture today, in this video, we're going to define energy as the capacity to do work or to produce heat. One of the most important characteristics of energy is that it is conserved. The law of conservation of energy states that energy can be converted from one form to another, but it can be neither created nor destroyed. That is, the energy of the universe is constant. Now, let's talk about the different types of energy we might encounter. We can divide all energy into two broad categories: kinetic energy and potential energy. Potential energy is energy due to position or composition, and there are various types. There's gravitational potential energy. This is the energy stored by objects due to their position above Earth's surface. There's elastic potential energy. That's energy stored when objects are stretched or compressed. There's nuclear potential energy. That's energy contained within the bonds that hold the nucleus together. And there's chemical potential energy, which is energy stored in chemical bonds between atoms and molecules. The second broad category is kinetic energy. The kinetic energy of an object is energy due to the motion of the object. And like potential energy, there is various types of kinetic energy. They include motion kinetic energy. This is the energy of an object in motion. Sound energy, that's the energy carried by sound waves, which is a form of mechanical energy through a medium. There's thermal energy, that's the collective energy of particles moving within a substance that contributes to its temperature. And there's electrical energy, that's energy carried by moving electric charges, often electrons, through a conductor. With this perspective of what energy is and how it exists in different forms, it's going to be important for us to go over terminology that's going to reappear in multiple lectures in this course. First and foremost, in thermodynamics, it is important to distinguish between the system and the surroundings. When we discuss reactions, we divide the universe into two parts: the system and the surroundings. The system is the part we're focused on. It's usually the reactants and products in a chemical reaction. The surroundings are everything else: the beaker, the room, the air, the lab equipment, so on and so forth. Understanding this boundary is important because energy always flows between the system and its surroundings. For example, if a reaction releases heat, the system is losing energy and the surroundings are gaining it. We can also classify systems based on how much interaction they have with their surrounding. So an isolated system, that won't be able to exchange matter or energy with the outside world. So think of an insulated, sealed container. Nothing gets in or out. So that's one type of system. Then there's a closed system. A closed system can exchange energy with the surroundings, but not matter. So this is common in a lot of lab setups. Finally, an open system can exchange both energy and matter. So think of a boiling pot of water on a stove, and it doesn't have a top on, right? Steam can escape into the air. So this is an open system where there's an exchange of both energy and matter. Further, as we start thinking about how to describe these systems, we also need to be precise about the properties we use to define them. Properties fall into two main categories: intensive and extensive properties. Intensive properties do not depend on how much material you have. So for example, the temperature of a glass of water, that's not going to change if you just pour it into a larger cup. Temperature, pressure, and density, those are examples of intensive properties. They all stay the same regardless of sample size. In contrast to this, extensive properties do depend on the amount of substance. So this is going to include things like volume, mass, number of moles, and energy. If you change the amount of substance, these values are going to change too. And this distinction between intensive and extensive properties, it matters because when we start deriving relationships in thermodynamics, intensive and extensive properties behave differently in equations. So that's important to keep in mind. Following that, we want to discuss the difference between state and path functions. A state function is a property that depends only on the initial and final states of the system, not the process that's used to get there. So think of it like elevation. If you hike from your base camp to the top of the mountain, the change in elevation is the same whether you take the steep trail or the winding one. In thermodynamics, common state functions include enthalpy, Gibbs free energy, internal energy, and entropy. We calculate these as final minus initial. And again, that's because a state function is a property that only depends on the initial and final states of the system. In contrast, a path function depends on the specific route taken. So these include work and heat. The total amount of work done or the heat transferred, that can vary depending on how the process occurs. Just like a longer trail is going to take more energy to hike. And we care about this because much of thermodynamics is about finding ways to calculate state functions like enthalpy or free energy from path-dependent measurements of work and heat. Now, to finish this introduction and this lecture, we're going to cover our last topic, which is temperature and the zeroth law of thermodynamics. Temperature is a measure of the thermal energy of a system. More specifically, it tells us the direction in which heat will flow when two systems are in contact. Heat always flows from the system with the higher temperature to the system with the lower temperature until they both reach equilibrium. Now, on the microscopic level, the temperature, that's directly related to the average kinetic energy of the particles in a system. The faster the particles move, the higher the temperature. This connection between particle motion and temperature, that's one of the bridges between microscopic mechanics and macroscopic thermodynamics. Now, temperature, it can be measured in different scales. We primarily see Fahrenheit, Celsius, and Kelvin. So in the Fahrenheit scale, this is very common in the United States, water freezes at 32 degrees and it boils at 212 degrees. In the Celsius scale, which is used in most of the world and in scientific work, water freezes at 0 and it boils at 100. The Kelvin scale is the absolute temperature scale used in thermodynamics. And we're going to dive into that scale a little bit more in the next chapter. But Kelvin has the same increment size as Celsius, but its 0 point is absolute zero. That's the theoretical temperature at which particle motion stops completely. On this scale, water freezes at 273 Kelvin and it boils at 373 Kelvin. We can really easily convert between these scales. So if we have Celsius and we want to get Fahrenheit, we use this equation, 9/5 multiplied by Celsius, and then we add 32. If we have Fahrenheit and we want to get Celsius, we're going to use this equation. So this is 5 divided by 9 multiplied by what's in the parentheses, Fahrenheit minus 32. And then if we have Celsius and we want to get Kelvin, it's simply Celsius plus 273.15. With this understanding, that temperature is a measurable property, let's go ahead and place it in the broader framework of thermodynamics. This is where the zeroth law of thermodynamics comes in. The zeroth law states that if system A is in thermal equilibrium with system B, and system B is in thermal equilibrium with system C, then system A must also be in thermal equilibrium with system C. And that might sound obvious, but it establishes the very foundation of temperature as a measurable and transitive property. Without this law, the idea of using a thermometer would not make sense. A thermometer works by reaching thermal equilibrium with a system. If equilibrium were not transitive, we could not trust that the thermometer's reading truly represents the temperature of the system being measured. So to bring everything together, what we've done in this first lecture is establish the language and the framework of thermodynamics. We defined what thermodynamics is and saw how it connects to real applications. We reviewed the SI system of units, which gives us the foundation for expressing physical quantities like force and pressure. We then introduced atomic and molecular masses, and we connected them to the mole. And finally, we defined energy, systems and surroundings, intensive and extensive properties, state and path functions, and the role of temperature and the zeroth law in describing thermal equilibrium. Every topic we cover from this point forward is going to build directly on those definitions and principles. So with that, we've completed this chapter. I hope it helps. Good luck, happy studying, and have a beautiful, beautiful day.